Okay, so here's the plan for today. We're going to go through kind of that whole assignment that I gave you all yesterday, make sure everybody's cool with that. If you want to, by the way, for those of you that have the laptops out, can you close those up? Thank you. So we're going to go through that, make sure everybody's cool, see if you have any questions at all, because that sheet is kind of like what the test is going to be. Okay, I'm going to talk about the test itself, and then I'm going to give you this blue sheet of paper. And typically what I do before the test is that I kind of give you a review, and then I send you the answer key to it, so that way you can know if you're doing it right or wrong. So that's what we're going to do towards the end. So with this one, what I'll do is I'll scan this, and then I just send it out to you as a PDF file to your emails. Okay? So that way it's not due, we'll talk about that later, but then you can have an idea. It's like, well, do I know what's going on? Okay, so let's talk about a couple of things. So we're just kind of, like I said, we're just going to go through this assignment, make sure everybody's cool with what we have going on, because this is what you have to be able to do for the test. So, even that first question, what determines the precision of a measuring device? Now look at your terminology, okay? So there's certain terms you have to have straight for the test tomorrow. One of them is the difference between precision and accuracy, okay? Because they're not the same thing. So can you always talk about the accuracy of a measurement? No, why not, Dalen?
Because there's not like a common value for everything.
Yeah, for some measurements there isn't an accepted value, okay? So if I talk about, well, how high is this tennis ball going to bounce after it hits my table? I don't know. I can't ask my phone that question. Like, what's the accepted height for how high a tennis ball is going to bounce? Okay, there is no accepted value. Now, if I said, hey, how fast should the tennis ball accelerate when I let go of it? Oh, that's an accepted value, because we know what the gravitational field is on Earth, and we know that that's going to create an acceleration of 9.8 meters per second squared. Okay, so I can't talk about the accuracy of how high it bounces, but I can talk about the accuracy of the acceleration when it falls. Okay, so that's the whole kicker. Can you ask your phone, and can you find an accepted value? If you can talk about accuracy. Now, you can always talk about precision. So let's say that you have two different measuring devices. One that's got 0.1, 0.2, 0.3. The other one has marks like this. There's 0.1, there's 0.2. Okay? So, Rebecca, which one's going to have a higher precision? The first one or the second one? Second one is, because that has more divisions. Now, here's the deal. If you were to make a measurement, and let's say both of these have a measurement of right here, and the other one is right there. Okay? So with this one, you have 0.1, 0.2, and the mark is here. So, Bhavani, if I gave you this measuring device, what would you give me as that measurement based upon this?
0.16.
Okay, 0.16. Now, let's talk about this. It's an excellent answer, by the way. So how is this 6 different from the 0 and the 1?
Well, I know the 0 and the 1 are like for sure, and then the 6 is an estimated guess.
Fantastic. It was kind of a surfer dude answer. I know the 0 and the 1 for sure, dude. My God. Okay? And it's like, I just had to guess the 6. Now, don't discount the 6, okay? It shows you the precision of that measuring device. Now, what you can't do is you can't say, oh, Mr. Burkham, I'm just a top-notch physics student, okay? I really like to measure. I'm going to put some zeros on the end of this, okay? Because I'm just that cool, right? Now, if you put zeros on the end of it, what does that imply?
That you know this.
Yeah, that you know the tenths, the hundredths, the thousandths, and you're guessing the 10,000s, okay? I can't do this. I can't make that measurement look better than what I have. Now, what if it had been exactly at that mark? If it had been exactly right there. Paige, what would I do?
0.10.
Perfect. So if it's exactly right there, I would have to write that as 0.10. So this is why zeros on the end of the measurement are significant, because they're conveying the precision of that measuring device. Because if Paige just puts 0.1, if she just puts 0.1, I'm going to think you've got a horrible measuring device. Man, you got a 0 and a 1, and that's it. This is it. You got a 0 and a 1. And you just kind of have to estimate, it's about 10. Okay? But that's why you have to put that 0 on the end, and that's why those zeros are significant on the end, because they show the precision of the measuring device. Okay? Now, what would you do with this one? Milkman. What would you do with that one?
I'd measure it 0.160.
0.160. That was kind of screwed up. That's actually 0.15. That's actually 0.16. So you're kind of in between there.
Oh, 0.155.
Okay, 0.155. All right. 0.155. And again, so this one is more precise because we know the tenths, we know the hundredths, and we're estimating the thousands. So that's what you have to realize. The more divisions this thing has, the more precise it is. Which one's going to be more accurate?
The bottom.
Why?
Because we have a more precise measuring device.
You can't talk about the accuracy of this measurement. Why?
Because there's no agreed upon.
I know what the accepted value is. Ask your phone. Hey, what's the accepted value for the measurement that Burkamp just put up on his board? Okay? There. All right. So you can't talk about the accuracy of either measurement because you don't know what the accepted value is. Now here's the other way that you can look at precision. And this is where the door swings the other way. Is that if I gave the two measuring devices, here's 0.1, here's 0.2, here's 0.3. And then you have this one, 0.1. So here's the other way that you can look at precision, is how well can a measurement be reproduced, okay? So if I gave Jackson and Tanner, and I gave them this measuring device, and I said, I want you guys to draw a line 0.15 widgets long. Okay, so they come in here, and Jackson might draw like that line, and Tanner might draw like that line, okay? Because of the fact that we're kind of estimating where that 0.5 is, there's going to be some discrepancy in that measurement. Okay, they're probably not, they might line up, but probably they're not going to exactly. Now, if I gave Milkman and Bovany this measuring device, and I said, I want you guys to draw a line 0.15 widgets long, you're going to be able to draw that line exactly to that mark, because you're going to know exactly where 0.15 is. So the other way to look at precision is that it's how well can a measurement be reproduced. The more divisions that you have, the more likely that measurement is going to be reproduced, because you're going to have more known values. So that's the other way that you can look at precision. Okay, and that kind of answers both questions 1 and 2 on that review. How does the last digit differ? Oh, that's an estimate. The other values are known. So in number 4, you're talking about velocity and distance. So, ray gun, what do you have as the independent variable on number 4?
Velocity.
Why?
Because you're changing the car's velocity, you can't change how, like, the braking speed.
Fantastic, okay? So velocity is my independent variable, right? Because that's what you control. And your stopping distance is dependent upon that value, okay? So you look at what you're going to control. So here's a simple example. Let's say that I'm going to use this plunger as an example, okay? So I'll want to play out a couple of scenarios. Scenario number one, I'm going to push this in just a little bit, and I see how far the car goes. Or push it in a little bit farther. I'm going to see how far it goes. I'm going to push it in really far, and then I see how far it goes. So I have two variables. I have the distance that I compress the plunger, and then I have how far it's going to go. Okay? So, which one is my independent variable? How far I compress the spring, or how far it rolls? Austin.
How far it rolls?
No. What am I controlling? Am I controlling how far I compress it, or am I controlling how far it rolls?
How far? No, how hard you compress it.
Yeah. So my independent variable is how much I compress that spring, because that's what I have control over. And then how far it rolls is dependent upon that distance that I compress the spring. Okay? So you look at, hey, what am I controlling? Oh, right, how far I push this in. So, when you get to this question of doing dimensional analysis, I promise you, you're going to have to do a couple of dimensional analysis problems on the test tomorrow. Okay, I promise you. So I want to make sure everybody's cool with this process. So what you've got is that you have D equals KV squared. So I'm going to, on the problem, I'm going to say, hey, do dimensional analysis, figure out what are the units of K. So it's the first thing you're going to do. Tanner. Yeah, so what's distance measured in? Oh, meters. I don't know what K is. Velocity is going to be in meters per second, but that's going to get squared. So when I square that, I get meters squared over,
Second square.
okay? Now and then I need to get K by itself. Here's your overriding theme that you need to list, that you need to remember about dimensional analysis. Dimensional analysis is a process, okay? It is a process. You want to show how things cancel out, okay? It isn't just, oh, a miracle happens and I get this answer, right? I cannot emphasize this enough. It is a process, okay? So, what I would do to get K by itself, I multiply by the reciprocal of meters squared over second squared. I multiply both sides. It's all about equality. What you do to one side, you have to do to the other. Ah, right. So that's second squared over meters squared, second squared over meters squared, right? So everything on the right side is going to cancel out. That goes away. What am I left with on this side? Well, that's going to cancel out one of those. I get second squared over meters. Okay? Now, if it had been meters over second squared, what would that represent if it had been meters over second squared? What is measured in meters per second squared? Acceleration. So if it had been meters per second squared, I would say it represents acceleration. But since it's second squared over meters, what does it represent? The inverse of acceleration. Okay, so the units of K represent the inverse of acceleration. So, and I promise you, if you hand in that test tomorrow, and you put it up there in the tray, and you haven't done dimensional analysis, well, something is wrong, okay? Something is horribly wrong. And I will tell you specifically, hey, do dimensional analysis. Okay, all right. So, on number 5, all you're doing is solving these variables, okay? Now, let's talk about number 6. So, you have V squared equals V naught squared plus 2AD. So, this is going to be one of the first big, like, physics equations that we're going to deal with. And this equation over the years has become known as that equation, which will make sense later on. So if I say, hey, we're going to use that equation is v squared equals v naught squared plus 2ad. Okay? It's the only one that has a name. Oh, that equation. All right. So you want to solve this for v naught. Now, remember, what's the difference between v naught and v? Milkman.
V naught is the initial velocity.
Fantastic. So this would be like, oh, I'm going to push the cart. The initial velocity is how fast it's going at the end. The final velocity is going to be how fast it's going at the when I look at it at a later point. So that might be speeding up. It might be slowing down. Okay, but so that's the difference. Initial velocity is how fast it's going at the beginning. Final velocity is how fast it's going at the end, and that's just v. So, how am I going to, I need to get v naught by itself. So what am I going to do?
I subtracted 2AD over this one.
I think that's wonderful. Minus 2AD, then what did you do?
Square rooted the V naught and then square rooted the whole thing.
Fantastic. Okay, now did you do anything else beyond that?
No.
No, you can't. You cannot, this is as far as you can go, okay? Because here's what kids try to do. They'll go, oh, the square root of v squared is v minus the square root of 2ad. You cannot do that, okay? Stop. Don't. No. Bad. Okay? Stop. Why can't you do that? Oh, come on. I'm going to go hunt down all your math teachers. Yes?
Order of operations.
Yeah, basically it's order of operations. Because this thing is being subtracted, you can't just bust out the square root of v squared. So this is as far as you can simplify this equation. Okay? You cannot simplify it any further than that. It's just v squared minus 2ad. Okay? You can't take it to the next step. Now, if it had been v squared times 2ad, if it had been v squared times 2ad, yes. And the square root of all of that, you could write that as v times the square root of 2ad. If they were multiplied together, you could do that. But since they're subtracted, you can't. Okay? That's as far as this can't. Boom. Stop. It's just v squared minus 2ad. That's all you can do. Okay? All right. Now, let's talk about number 8. Okay? So period equals 2 pi times the square root of L over G. So how this is going to play out like you have a pendulum. Okay? So it's going to swing back and forth like this. Right? So period is going to be the time it takes to go from one side over to the other side. Okay? Like this. And L is your length, G is your gravitational acceleration. So the first thing you want to do is solve this thing for L. So this is what I would do, okay? I divide both sides by 2 pi, okay? And then I need to get rid of that radical, so I'm going to square both sides. And then I'd have t squared over 4 pi squared equals L over G. Now, personally, I hate fractions, okay? I've never just been a fan. I know they're a necessary evil, but I've just never really been a fan of fractions, okay? So what I would do, hopefully at some point in your mathematical careers, you've learned how to like cross multiply, right? Everybody cool with cross multiplication, right? So all I'm going to do is I'm going to take this times this equals this times this. If you've never done cross multiplication, you all come talk to me. It's a wonderful tool, right? So I'm going to have gt squared equaling 4 pi squared L. Now the beauty of this one is that once you get this equation like this, then it becomes very simple to solve for any equation. You can solve this thing for G, you can solve it for T, you can solve it for L. Now, let me give you a little thing that you can do to check this. If this equation is right, should you have the same units on both sides? Yeah, because if you don't have the same units on both sides, this equality doesn't mean anything. Okay? It's not correct. So, let's do a little process of dimensional analysis. G is going to be an acceleration measured in what units?
Meters per second squared.
Meters per second squared. Okay. That's meters per second squared. T is going to be in seconds. That's going to get,
Squared.
so we're going to have second squared. So I'm going to have meters per second squared times second squared. I get
Meters.
meters. Okay, so this side gets me meters. What's the only thing that has any units at all over here?
Like,
Length, and that's going to be in
meter,
meters. So guess what? Meters equals
Meters.
meters, the equation is valid. Okay? If I didn't get the same units on both sides, I've done something horribly wrong. Okay? Because I can't keep that equality sign in there. And again, I emphasize this. The sooner you embrace this idea of using units to check that an equation is valid, the deeper you're going to see into these relationships. Okay? But again, that's tough from my perspective from this side of the table. Because for 12 years of education, you guys have been stressed, did you get the right answer? Okay, so the education process up to honors physics with Mr. Burkamp has been, hey, did I get the answer right? And that's what you all focused on. Unfortunately, you've been done a huge disservice. They should have been emphasizing the process, because if you pay attention to the process, the answer will take care of itself. And that's true of life as well. If you pay attention to the little things that you do in life, the big things will take care of themselves. Okay? It's true. Because I got an assignment. Winning, work ethics, whatever, becomes a habit. And every time you quit on anything in life, it becomes easier. That becomes your habit. Oh, I'm just going to, that's a tough problem, I'm just going to quit. That becomes your mindset. If you have this mindset that says, you know, I'm going to work my way through this. And if that becomes your mindset, then that becomes your habit. That becomes, oh, this is how I'm going to approach life. Because, and it goes both ways. And grant me the wisdom of 55 years on this earth, and I've seen a lot, and I've done a lot in this world. And you see successful people. Successful people go, I'm going to find a way to make this thing work. People that aren't successful, quitting becomes their habit. So the sooner that you embrace this idea and say, well, hey, it was just one problem. You're right, it's one problem on an assignment. But then that becomes your habit. So if you look at successful people across all aspects, business, athletes, musicians, whatever it is, the most common trait that they all have isn't intelligence. It isn't financial wealth that they came from. It's what you call grit. Do you have the capacity to work through a problem? So the most successful people across all aspects of society are the people that have grit. Find a way to work through the problem. And so if nothing else, that's what I hope you get from this class. Like, hey, yeah, it's going to be tough, but I'm going to work through it, and there comes a satisfaction from that process of working through it. So dimensional analysis, you know, what does that have to do with life? What it has to do with life is that if you pay attention to the little things, the big things will take care of themselves. Okay, so you want to solve this for L. So you're going to have, come back here, GT squared over 4 pi squared. So this should be your answer for 8a, okay? And that's going to be this length. So then you're going to plug in these numbers, and your answer to 8b, when you're going to find the length of that pendulum, should be something around 0.6 meters, okay? So what that means is if you build a pendulum about yay long, about 0.6 meters, that should have a pendulum or that should have a period of 1.5 seconds, okay? Cool with that. Now, when you get to C, you're going to solve this equation for G. So what I would do, because you already have, if you already have this, then you don't have to start over from scratch. Just go to this. If you already have this, then it becomes very easy to solve for little g. So, quick lesson in history. So, the Apollo 11 mission was the first one that actually landed on the moon. And we'll go through the math on this later on. But one of the first things that they did as a science experiment is that they set up a pendulum. And they set up the pendulum and they measured the period of the pendulum and they knew the length. And it's like, really? You guys went all the way to the moon to set up a pendulum. That was kind of a waste of money. But here's why this is important. So, what you can do, once you know the period of the pendulum and the length, you can calculate the gravitational acceleration. So your answer to D should be around 3.8 meters per second squared. So later on you'll see how this works. But once you know the value of little g, then you can find the mass of the planet that you're on. So this is how we found the mass of the Earth, is that we literally set up a pendulum, we measured the value of little g, we knew the radius of the Earth, we solved for the mass of the Earth. That's what they did with the moon. So we didn't know the mass of the moon when we went there. We had a pretty good idea of what it was going to be, but we didn't know for certain because we didn't know what the structure of the moon was. So when they landed on the moon, they set up the pendulum, they measured the period, they calculated little g. They did a calculation just like this. Then once they got little g, then they could work backwards and find the mass of the moon. Okay, so that's why. So if you ever get a job exploring interplanetary space, and your job as a science experiment officer is like, oh, we have to find the mass of this moon that we landed on. Take along a pendulum, set it up, measure the pendulum, measure the period, measure the length, boom, you get little g, boom, you can find the mass of the moon. Okay, so that's the significance of that calculation. All right. So on number 9 and 10, I promise you, on the test tomorrow, there's going to be a problem like 9 or 10. Okay, so I want to make sure everybody's cool with this. If you hand in your test tomorrow and you haven't done a calculation with some planet moving or spinning on its axis, you have done something horribly wrong. And on the test tomorrow, I will give you that equation, that V equals 2 pi r over t. I will give you this equation. Don't memorize it. It's going to be on the test. I want to say, hey, you just have to know how to use this equation. But again, don't flip out and go, oh man, that's a tough equation. All it is distance divided by time. All we did is we're saying, okay, 2 pi r, I swing this thing around over my head, I measure the radius, I figure out how long it takes for it to go around, I'm going to take the distance that it travels and I'm going to divide it by how long it takes. It's the exact same thing of what we did with Jackson yesterday. Jackson went out and he ran in the hallway. We measured how far he ran and we divided it by how long it took. So this equation is nothing more than Jackson running around in a circle. Okay? So don't flip out and go, oh, that's tough. No, it's not. Okay? It's just distance divided by time. But like I said, I'll give you the equation, so don't flip out. So what you want to do is pay attention to the units. So you got 2 pi. I already gave you the radius, 1.50 times 10 to the 8th kilometers. Okay? Now, how long does it take for the Earth, for our rock, to go around our star? 365 days. But what are you going to do with the days, Tanner? 1 day is 24 hours. Okay? So there you go. So that first answer on number 9 should be something times 10 to the 5th kilometers per hour. Okay? Like 1 and 1 and some change times 10 to the 5th kilometers per hour. Okay? Now, the next thing you're going to do is you're going to change that into meters per second. Okay? And again, I promise you, you're going to do a conversion from kilometers per hour into meters per second. If you hand in your test tomorrow and you haven't done that, you have done something horribly wrong. Okay? So, just take that 1 times 10 to the 5th kilometers, put that over 1 hour. 1 kilometer is 1,000 meters. 1 hour is 3,600 seconds. You can lop off the zeros, multiply by 10, divide by 36. And that's the short version. And again, I promise you, tomorrow, if you have not converted a number from kilometers per hour into meters per second, stop. You've missed something, okay? Now, because you're multiplying by 10 and you're dividing by 36, what do you know about this answer compared to your value of kilometers per hour? Is it going to be bigger or smaller?
Smaller.
Smaller. So when you convert from kilometers per hour into meters per second, this numeric answer here has to be smaller than what you started with. Okay, it's a simple check. Oh, divide by 10, or multiply by 10, divide by 36. Right, okay. If you don't get an answer smaller than that, you've done something horribly wrong. Okay, so it's just a simple quick check that you can do. Now, let's talk about number 11, or number 10. So here's the difference on number 10. So what we're saying on number 10 is that here's the Earth and here's the penguin. Okay, I don't know why, but I have it. So the penguin is here and he's really, really lost and he's in the middle of Africa. Okay, and this penguin is going around like this, right? Coming around and it's going to come back over here. And we want to figure out how fast is that penguin moving sitting on this spinning rock that we call home. Okay? So, it's the exact same idea. So if you think about it, as that penguin goes around, that penguin is going to travel the circumference of the Earth. Okay? Just like the Earth goes around the sun, there's a certain path that it travels. The same thing is here. So as this penguin goes around, because we have a spinning rock, and thank God we do. If the Earth didn't spin, it would really be horrible because we'd have one side of the Earth that was always facing the sun, and we'd have the other side of the Earth that was in eternal darkness. So you'd have one side of the Earth being really, really hot, the other side being really, really cold. And that's all we'd have. Sunlight, darkness, that's it. So, as a matter of fact, the Earth is actually slowing down as it spins. Don't go, oh, I feel it slowing down. No, you don't. No, you don't. But it is. They think when the Earth first formed, a day was like 12 hours. So, when the Earth first formed, the Earth was spinning about twice as fast as it does right now. So, it would be really, really weird because, oh man, instead of like having like 12 hours of darkness and 12 hours of light, you have like 6 hours and 6 hours. It's like, whoa, short nights, long days. Okay. So, on number 10, you're going to use the same idea. You're going to 2 pi r over t. So, how long does it take for our rock to spin once on its axis?
24 hours.
24 hours, okay? So, you do this, you're going to get like something times 10 to the 3rd kilometers per hour. And then that second answer on number 10 should be 463 meters per second. So this presented a problem, okay? This presented a problem. Because this is the whole debate, is the Earth stationary or is the Earth spinning, and what's our location in the solar system. So they've known the radius of the Earth for quite a while. And it was kind of cool how they did it. There's a certain day this is in the Middle East, and there was a tower. And on a certain day of the year, this tower did not cast a shadow. Okay, so the sunlight came straight down on this particular tower. So the sunlight was coming in like this. But they knew there was another tower quite a ways away, and that did cast a shadow. So what they did, it was kind of some simple geometry. They said, okay, well, this tower doesn't cast a shadow, but this tower does. So they worked out, they said, okay, what's the angle of that shadow? And they knew the distance between these 2 points. So then what they were able to do is basically work backwards, and they would figure out this portion of the arc length of the radius of the Earth, and they used that to figure out the entire radius of the Earth, and then they could find the radius. So they knew the entire circumference, they could work out the radius. It was kind of cool how they did it. It was pretty clever, actually. And so when you get into this argument with the Earth spinning, and people overblow this, you know, people make it look like this is this huge debate. In reality, almost all the scientific community in antiquity accepted the fact that the Earth was spinning. Okay, they just made sense, and the Earth was round. They kind of accepted that. But here's the problem with this answer of 463 meters per second. The problem with this answer is that it's faster than the speed of sound. Okay, the speed of sound is like 343 meters per second. That's 463 meters per second. So that's like 100 meters per second faster than the speed of sound, which kind of creates a problem. But here's the other issue. I'm guessing at some point when you were younger, and you actually went outside to play, and you had fun, and life was simple, okay, before you got cell phones and your entire life was looking at TikTok videos. But when you actually went out, yeah, and you all laugh, but it's true, okay? Like, so what did I do yesterday? Like, your typical adult spends a third of their waking hours using some type of app on their phone, okay? Which is a stunning number if you think about it. It's like, wow, a third of my waking hours, I'm staring at something on my phone, okay? It's like, go out and experience life. So, assuming that at some point in your life you rode a bicycle, okay, it's like, oh yeah, I remember those times, okay? And let's say that you had a puddle of water, and against the advice of your parental units, you rode your bike through the puddle of water, okay? So what happened to the water that was on that bicycle tire after you rode through the puddle? What did it do? Did it stay on there, or did it go flying off? Paige, were you ever a rebel and did this? Okay. What did the water do? It goes flying off. Same thing with your car tires, right? You drive through water, okay, and the water goes flying off. So this was one of the debates, is that if the Earth is actually spinning that fast, 463 meters per second, so your tires are going at about probably maybe 20 meters per second, and the water goes flying off. So if the Earth is actually spinning that fast, how can we have oceans? Why hasn't all this water gone flying off the surface of the Earth? Tanner. Yeah. Well, later on we'll do the calculations. Is that we have enough of a gravitational field to hold water on. Okay? And it's quite a bit stronger. It's more than enough to hold it on. But that was one of the debates, like, okay, if the Earth is really spinning that fast, why do we have oceans? Now, here's the other question relating to this number, is that we have an atmosphere, okay, thank God that we do, and, or otherwise we wouldn't be here having this discussion. So the question is as the Earth spins, okay, so imagine my hand is like our atmosphere. So here's the question. As the Earth spins on its axis, my hand represents the atmosphere. Is the atmosphere moving with the Earth as it spins? Or is the air stationary and we're spinning through a stationary air mass? Okay, so that was one of the big questions. does the atmosphere move with the Earth as it spins? Or is the air stationary and then we move through the air? What do you think?
I think it moves with us.
Huh?
I think it moves with us
Why?
because air still has friction to be brought along with the earth, and like I mean, like that's how we get wind systems, right? Like, the earth standing, like the wind heating up, and
Okay? So you're saying the Earth moves with, because, let's think about this. Jackson,
If it moved with us, would like clouds move, stay in the same place?
yeah?
Okay, so why do clouds move?
Okay. We'll get there, all right? It's good, it's a good argument, okay? So let's back up. Let's say that we're going to assume that the Earth spins, but our atmosphere doesn't move with us. So this is kind of like what Jackson brought up. So let's say, and again, back in your misspent youths, okay? And Mom was driving, and you were on your way to basketball practice or soccer practice or whatever you were doing, okay? And then again, this is back when you were willing to experience nature. And does anybody ever like roll down the window and stick your hand outside the window when you're driving? Okay, yeah, okay, you did this, right? It's like, this is cool, right? If you've never done that, you have completely missed out on a certain cool aspect of life. If you have never rolled down a window and put your hand out and kind of done this as it goes through the air, that's your homework assignment, okay? If you've never done that, you need to experience that feeling, okay? Now, so that's your car, let's say, is moving at 40 miles per hour, and which is about 20 meters per second. So if you've ever put your hand out there in air that's, you're moving through air and 20 meters per second, and you feel kind of this wind pushing you back, right? Imagine that our atmosphere wasn't moving with us, and you would stick your hand out into air that was moving at 463 meters per second. Okay, Jackson, what do you think is going to happen?
I don't know.
Probably bad things are going to happen, right? You stick your hand, boom, okay, right? Trees, boom, they'd be all laid down. Birds couldn't fly. It would be mass hysteria, right? So if their atmosphere was stationary and we were moving through at 463 meters per second, every time you stepped outside, you'd basically be knocked down, okay? We couldn't build anything. Now, Jackson had an interesting point, though. So, well, sometimes clouds move. So, our atmosphere isn't static. It is moving with us, but you have areas of that move. This is why you have wind, because you have high and low pressure systems. So, air moves from high pressure systems to low pressure systems. So, like this weekend, there's a pretty good chance of snow on Friday night and Saturday morning, okay? Bad weather is associated with low pressure systems. So, and then Friday afternoon, we're supposed to have really, really strong winds. Excuse me, Saturday afternoon, we're supposed to have pretty strong winds. So, anytime you have strong winds, it's because you have what's called a pressure gradient between the high pressure system and the low pressure system. So, the reason that the clouds appear to move is because you have aspects of the atmosphere that are moving at different speed relative to us. But overall, the atmosphere is moving with us, okay? So, there's that. Okay, I promise you there's going to be a question like number 11 on the test. I promise you there's going to be one like number 11. I'm going to give you a half sheet of graph paper and I'm going to ask you to draw that. So where are you going to put force?
On the x-axis.
Why?
Because it's the independent variable.
That's what you control. And I'm going to put that as kilograms meters per second squared. You can have acceleration here in meters per second squared. Okay, and again, if you hand in your test tomorrow and you have not graphed force and acceleration, you have done something horribly wrong. It's going to start at 0, 0. You're going to draw a line of best fit. You think I'm going to ask you to find the slope of the line? Mm-hmm. Yep. You think you're going to have to show your work?
Yeah.
Yep. You think you have to have units on that slope? Mm-hmm. Yep. Promise you. Promise you, promise you, promise you. So what you should get on 11A, when you find the slope of that line, you should get 0.200. Now, if that's all you put as a slope of 0.200, why is that bad? Yes?
You didn't show your units.
What'd you say?
You didn't include your units.
Yeah, I know what the units are. I don't know, is it $0.2? Is it 0.2 ducks? What is it? Okay? But again, this is why you have to look at this whole thing as one big idea. So, you got meters per second squared when your slope changing y over changing x. And you're going to divide that by kilograms meters per second squared. Those are going to cancel out. You're going to get 1 over kilograms. If you want to get fancy, you can put that as kg to the minus 1. It's the same thing. So at the end of these units, you can either put 1 over kilograms or you can put kg to the minus 1. I don't care. It doesn't make me any difference. But that's why when you get to B, I say what physical quantity is shown by the slope. If it had been kilograms, what would the slope represent? Mass. But since it's 1 over kilograms, the slope represents the inverse of mass. Okay? There you go. Now, when you get to C, where it says write the general equation for the line, this is a linear function where you have y equals mx plus b. Is there going to be a y-intercept?
No,
No. Why?
it doesn't start at 0, 0, but
It doesn't hit the Y.
like it doesn't, yeah, I don't know, last time we talked about it, you said that, and then it doesn't touch anything on the Y.
Okay, guys, here's the reason why. I got my cart. What do I have to do to make that thing accelerate?
Give it a force.
I have to give it a force. If I don't apply a force, I don't get
Accelerate.
acceleration. So this is why it starts at 0, 0. No force, no acceleration. I apply a force, hey, I get an acceleration. The more force that I apply, the more acceleration that I get. Okay. So that's just physically, this is why we don't have one, because if I don't apply a force, I don't get an acceleration. Okay. Now, so one of the things that then, because this is y equals mx plus b, what do you graph on the y-axis? Acceleration or force? Acceleration. So you're going to have a equals 0.200, 1 over kilograms times force. Don't worry about the y-intercept because there isn't a y-intercept. So make sure that you put the units with that slope. Okay, and I'm going to tell you that explicitly in the instructions. I'm going to tell you, put the units with the slope, okay, or otherwise it doesn't have any meaning. So then on D, how much force would be needed to produce an acceleration of 6.5 meters per second squared? Your answer to 11D should be in the low 30 newtons, okay? And again, here's what you can do. You can use your data to see if it makes any sense. Oh, you want an acceleration of 6.5 meters per second squared. Look at your data, okay? An acceleration of 6 meters per second squared required a force of 30 newtons. So if you want a little bit more than 6 meters per second squared, you got to figure your force is going to be a little bit bigger than 30. So you can look at your data to see, wow, does this make sense? Does it fit within that paradigm? Now, I promise you I'm going to ask you a question like this. Mark my words. I'm going to have, and this is how it's going to play out. I'm going to have you draw the graph, boom, fog kick, slope, all this good stuff. And this is going to be on the bottom of the front page. I'll even tell you where this is going to be. This is going to be on the bottom of the front page. And I'm going to ask you, I'm going to say one of two things. I'm going to say, how would that slope change if the mass of the object was bigger? Or I'm going to say, how would the slope change if we decrease the mass? Now, there's two approaches you can take. Let's say we're going to increase the mass. So one option is that you say, okay, I'm going to take this cart and I'm going to put more blocks on it. I apply the same force. What's going to happen to the acceleration? It's going to go down. So one option is that you say, I apply the same force, I'm going to get a smaller acceleration. Okay? That's one option. And again, when you answer that question, keep one variable the same. say, oh, for a given amount of force, there is going to be less acceleration. Or to get the same acceleration, that's going to require more force. Okay? Pick one, keep it the same, change the other. Here's the other thing that you can do. And this is if you're more of a math nerd, okay? But it works. So if you realize the slope represents the inverse of mass, so if you make the mass bigger, because you're taking about the inverse of it, so if you have 2 kilograms, and I say, oh, take the inverse of that, oh, that becomes 1 over 2 kilograms. If you go to 5 kilograms and you take the inverse of that, that becomes 1/5 kilograms. So because the slope represents the inverse of mass, as the mass gets bigger, the slope, the inverse of that becomes a smaller number, the slope becomes flatter. I don't care how you answer the question. You can do the mathematical side of it and go, oh, right, it's the inverse of mass, right, it's going to become flatter. Or you can say, for the same force, I'm going to get less acceleration. I don't care. Pick one, okay? All right, now let's talk about number 12. So 12 is an interesting concept. So what we're talking about on number 12 is that if you could take a beam of light and stand at the equator and turn on this beam of light, and you can make it follow the circumference of the Earth, which it won't because it's going to go in a straight line, but if you could, the first thing you want to figure out is how long it's going to take for that beam of light to go around. So, here's the deal. All you're going to do, and think this through. Oh, right. This beam of light is going to travel the circumference of the Earth. Oh, right. Circumference of the Earth is 2 pi r. So if I know 2 pi r, I can figure out how far it has to go. Okay, cool, right? So basically, I'm trying to find the time. And I gave you the speed of light. 3.00 times 10 to the 8th meters per second. So basically, come back up here to this and go, oh, that's 2 pi r over t. I gave you the velocity, so you know how fast it's going. You can use this to figure out how far the beam of light has to travel. And then you can solve this thing for t. Okay? So Bhavani, I want you to solve this equation for t. What are you going to do?
You can multiply t and get it on the other side.
Yes.
And then divide by velocity.
Fantastic. Okay? Give a shout out to your algebra teachers. So I'm going to multiply by t, and then I'm going to divide back. So I'm going to get t equals 2 pi r over v. Okay? Now, here's where I was a jerk. I was a little bit of a jerk when I typed out this question. What units did I give you the radius in?
Kilometers.
Kilometers. So you have kilometers on top, but the velocity is in.
Liters per second.
So you have to make a choice. And again, this is why you pay attention to the units. Here's the choice that you have to make amongst many that you're going to make in this world. You either need to change the kilometers into meters by multiplying by 1,000, or change this into kilometers per second by dividing by 1,000. Okay? I don't care which one you do. But you, and this is, and the reason I did this is to force you to pay attention to the units. Because if you had put in the units, you would have looked at that and went, wow, God, Brookham's a jerk. He gave us kilometers and he gave us meters per second. But that's why you pay attention to the units. Okay? Because if you just blissfully write down the unit, or write down the numbers, and you don't pay attention to the units, bad things are going to happen. Okay? So what you should get is you should get an answer of around 0.1 seconds. Okay? So 0.1 seconds is about like this. So here's the significance of why this is so fast. This beam of light, keep in mind, is going all the way around the Earth. So when you turn on that flashlight and you snap your fingers, that's how long it's going to take for that beam of light to go all the way around the Earth and come back to you. That amount of time. Okay? So this is why measuring the speed of light is so difficult to do, because it's such a high number in terms of that velocity. Okay, now here's when you pay attention to units. So technically what you get out of 12A is seconds per revolution. That tells you how long it takes to make one revolution. Okay? So what you're asked for on B is in 1 second, how many times can a beam of light travel around the Earth? So what you find on A is period. That's so many seconds per revolution. What you want on B is frequency. So over on your big dog equation sheet, I have this, that period is equal to the inverse of frequency. So let me kind of give you an example. So I take this rubber stopper and I swing it around over my head, right? And I'm going pretty slow, okay? So that takes a long time for that rubber stopper to go around. Tanner's getting hypnotized here. It's just funny watching Tanner's going like this, okay? So I'm going pretty slow, and Tanner's back there counting how many times it goes past per second, okay? It's going pretty slow, not a lot of revolutions per second, but it takes a long time to go around. Now, if I go faster like this, okay, now what's happened to the amount of time it takes for one revolution? It's become less, but what's happened to the number of revolutions per second? It's gone faster, okay? So I can go really slow and have a long time for this to go around, but I'm not going to see the stopper go past very often. I go a lot faster, right? So the amount of time for one revolution has gone down, but the times that it goes around per second goes up. So this is why these are inverses of each other. So if you want to calculate frequency, and we're going to do the same algebraic movement that Bhavani did just a second ago, I'm going to multiply by frequency, and then I'm going to divide back by period. So frequency is the inverse of period. Now, this is where the magic happens in terms of units. So we just found period, seconds per revolution. So this is where the magic happens. It really isn't magic, but it sounds cool. So I'm going to take 1 over seconds per revolution. This is why you do dimensional analysis. So I'm going to take 1 over seconds per revolution. Guess what? The revolutions flip up because it's in the denominator of the denominator. Guess what? You get revolutions per second. So your answer to 12B should be around 7.5. Okay? So here's the cool thing about this, is that if you could turn on that beam of light and have it go all the way around the Earth, and if you could count the number of times that you see that beam of light pass you in 1 second, it'd be like 7. So just try to count to 7 in 1 second. What if I said 7? Okay? That's how many times you would see that beam of light go all the way around the Earth and pass you. It's an incredibly fast number. So every second, you go around about 7 times. So on 12A, that answer should be around 0.1. And your answer to 12B should be around 7. Okay? If you do that right. Now, the other thing, speaking of this equation, is number 13. Milkman.
Just a quick question. So for the significant digits,
Yep.
it's only the stuff in the scientific notation, right?
Well, yeah, so if you look at what's happening on number 12, I've given you two different measurements. I've given you 6.37 times 10 to the third, and I've given you 3.00 times 10 to the eighth. In both of these, how many significant digits do you have?
3.
3. So all of your answers should have 3 significant digits. Okay? All right. I promise you, you're going to have a question like number 13. So here's what we've got. So this is the equation that we've dealt with. It's old hat at this point. It's like, yeah, Mr. Burkamp, I got that. Okay. And so here's what, and again, there's two ways that you can work this problem. Okay? There's two ways. One is that you can do smash mouth physics. So what I'm saying on this one, if the radius is constant and the period is doubled, what will happen to the velocity? Okay? So one option is that you make up numbers. If you like smash mouth physics, you go, here's my initial velocity, 2 pi times 1 meter. What's the easiest value we could use for t? 1 second. Okay, right? So basically I get 2 pi meters per second. Okay, there we go. Now, what's going to happen then, if the radius is constant, I'm going to double the period. So my new velocity is going to be 2 pi times 1 meter, but then I'm going to divide by 2 seconds. Oh, okay, that cancels out. I get pi meters per second. So what's happened to my velocity? Has it increased or decreased?
Decrease.
So it's half of what it was. Okay? So if you like numbers, put in numbers. Oh, okay, right. It's going to become half of what it is. If you're a math nerd, okay, if you're a math nerd, let's hear it from the math nerds. You go, oh, okay, I can play this game, Mr. Burkamp. That's 2 pi r over t. Cool, right? Here we go. So my new velocity is going to be 2 pi r, but then I'm going to divide by 2t. So instead of dividing by t, I'm going to divide by 2t, so what's going to happen to my velocity? It's going to become half as much. Okay? Tanner's back there kind of doing this physics gang sign. Yo, sup, half, yo. Right? So, it's just funny. You're like, yo. Good. Flash of the half sign. Then on the next one, what's going to happen to the velocity? The period is constant, but the radius is doubled. Okay? So that one, again, you can do the same thing. You can go 2 pi r over t, and then the new one is going to be 2 pi times 2r over t. You double the radius, what's going to happen to the velocity? It's going to double. Okay? So I promise you, you're going to have a question like that on the test. I don't care how you do it. If you want to put in numbers, make a comparison, cool. Doesn't make me any difference. Okay? So, you know you're going to have, here's what's going to happen. Make sure that you know the MKS systems, meters, kilograms, seconds. Make sure that you know the 3 derived units, velocity, meters per second squared, and force. Okay? Home run deal. Make sure that you know the difference between independent, dependent variables. Okay? Which one you control, which one is dependent. Make sure that you know the difference between precision and accuracy. Okay? Make sure that you can do the process of dimensional analysis. Make sure that you can graph force and acceleration. Make sure that you can do operations with significant digits. Now, let's say I gave you this question. Hypothetically, let's say I gave you this question. So I want you to listen to this very carefully. True or false? You're comparing 2 measurements. Okay? So true or false? Comparison of 2 measurements. The value with the largest number of significant digits is also the most precise. Okay, so it's a true or false statement. You're comparing 2 measurements. The one that has the largest number of significant digits is also the most precise measurement. True or false? Jackson.
Not always, right?
Why?
Well, because
Give me an example. Justify your answer.
because you could have nothing behind the decimal, like on the right side.
Yeah.
So,
So maybe like 2,120.
versus, I think it were 2.102.
versus if it was what?
2.20.
2.20.
Whatever, yeah.
So yeah, there you go, right? So, actually, let's just make that 2.2. So, how many significant digits does this have? 3. I don't count that 0. Why?
Cause you count this left.
No decimal place, right? No decimal place, sweep left. 2.2 has 2 significant digits. So this has fewer number of significant digits, but it's more precise because this goes out to the 10th place. Okay? So that's why I said the number of significant digits isn't necessarily a reflection of the precision of the measuring device. So you could have a really, really big number, but that doesn't mean it's very precise. So if you're looking like to the distance to the moon, oh, the distance to the moon is 3,844. Okay, meters. That's the distance to the moon. It's a really, really big number. Okay, so it's a really, really big measurement, but that isn't necessarily very precise. You say, okay, hey, I'm going to measure the diameter or the distance across a binder clip. Oh, that's 0.150 meters. Okay, so this is much more precise, but you're also only measuring a binder clip. Okay, so that's how you want to think this through. Okay, Austin, stop that for just a second. So let me explain what I just gave you. This is not due. Okay, I'm going to send out the answer key to this assignment. Okay, so don't flip out. Go, oh my God, I got to hand this in. So this is not due. I'm going to send you the answer key. But this is going to kind of tell you, wow, how am I doing with this process of significant figures and conversions and things like that. On that green sheet that I gave you all yesterday, if you want to hold on to that and hand it in tomorrow and use that as a review, you can. Okay? If you're done with it and you feel good and you want to go ahead and hand it in, you can. I'll have it graded by tomorrow morning, so if you want to come in and get it and see how you did, that's fine. I don't care. It doesn't make me any difference. If you want to hand it in, great. If you want to hold on to it, whatever works for you. Okay? And it won't be late if you hand it in tomorrow, because I don't care. So on the test, it's going to be one page, front to back. Okay? The first probably maybe 8-10 questions are going to be multiple choice. I'm going to say, hey, you know, that's going to be kind of your definition kind of things. Oh, what are the units for velocity? What are the units for acceleration? What are the units for force? What's precision? What's accuracy? So that's where you're going to kind of know general knowledge. The bottom of the front page is where you're going to have the force and acceleration graph. Okay? I'm going to give you a half sheet of graph paper, put the force on one axis, put acceleration on the other. You got to know which one goes where. You're going to find the slope of the line, all that kind of thing. Okay? On the back side, I'm going to give you like an equation. I'm going to ask you to solve it just like you did on the screen sheet. Okay? I'm going to give you the next problem is I'm going to give you a different equation. I'm going to say use dimensional analysis to prove that the equation is valid. Next big problem is going to be, I'm going to pick a planet, Mars, Jupiter, whatever, and I'm going to say calculate the velocity in kilometers per hour and calculate the velocity in meters per second. Okay? Then you're going to have like another dimensional analysis problem to do. Okay? And then you're going to have some questions on that. So it's going to be one page, front to back. Okay? It would be the shortest test you're ever going to have in this class. You will also, what will happen is I will give you a laminated version of the Big Dog equation sheet. So if you flip out and go, oh, I forgot what kilo means, okay? That's going to be on there. Oh, I don't know the circumference of a circle. You're going to have that, okay? So you will have that, or you have a laminated version, not your own, but I will give you that. Also, when we take tests, I want you to spread out, so I'm only going to have one person per table when you take the test. So you can either do like rock, paper, scissors, to figure out who's going to move. You can go to the back of the room, you can sit at the desk, you can move up here. So I only want one person. It's not as crowded and it's just more laid back, and you have your space, okay? So, and yes, I'm also gonna give you a sheet of graph paper, so don't worry about reading graph paper. So you're gonna have Tanner,
Are we allowed to use calculators?
bring what?
Are we allowed to use calculators?
Yes, you can. Now, my high school teacher in physics did not allow us to use calculators on the test, which really sucked, okay? Reagan's going, oh God, no, this is horrible, okay? Yes, well, yes, you can use your calculators, okay? I'm testing your knowledge of physics, not your ability to do calculations by hand, okay? So there's that. When you get to this question on number 12, on the sheet that I just gave out, you're trying to figure out how many hydrogen atoms it would take stacked side by side to equal the length of 1 meter. So let's talk about, let me kind of lay that out of what's going to happen. So you're going to have a length of 1 meter, and you're going to figure out how many hydrogen atoms you would have to stack up to equal 1 meter. Now, is a hydrogen atom pretty small or pretty big? Really small, right? So, do you think you're going to have, is it going to take a lot of hydrogen atoms to equal 1 meter, or not so many? It's going to take a lot, right? Each one's really small, right? So they're going to kind of stack up all these hydrogen atoms. So here's, again, where you think this is true in terms of dimensional analysis. At the end of the day, when you get to number 12, your answer needs to be in atoms. Okay, that's what the units that you're going to have. So you know you have a length of 1 meter. Okay, so you have this length. Now let's play the what if game. Okay, let's play the what if game. If the radius of a hydrogen atom was 0.25 meters, which would be really big. It's like, this is a big honking hydrogen atom. Okay, water would have a whole new thing. So if the radius was 0.25 meters, how many would it take to equal 1 meter?
4.
4? Everybody cool with 4? Cool? Don't be.